Hello and welcome. Today we're diving deep into the world of electrochemistry. Now, that might sound complicated, but really, it's the invisible force connecting the chemical reactions in something like a battery to the electricity that powers, well, pretty much everything. So let's get into it. So, have you ever stopped to think about it? How do chemical reactions power your phone, get your car started, or even cause a piece of metal to rust? It seems like three totally different things, right? Well, it turns out they're all powered by the exact same fundamental principles. Stick with me, and you'll see how it all connects. So here's our game plan. We're going to start with that basic link between chemicals and electricity. Then we'll look at how electricity literally swims through a liquid, which is so cool. After that, we'll figure out how to predict chemical energy. And then we'll tie it all back to the stuff you see every day, like batteries and rust.
Okay, so at its heart, electrochemistry is really a two-way street. On one side, you have chemical reactions that just happen on their own, and we can harness that energy to create electricity. But on the other side, we can use electricity to force chemical reactions to happen that wouldn't normally. That one idea, that's the key to everything we're going to talk about.
Right, we all get that electricity zips through metal wires, and that's just electrons on the move. But what happens when you're talking about a liquid, like the stuff sloshing around inside a battery? How does electricity get through that? Well, it's a whole different ballgame. And here's the big secret. In a solution, it's not these tiny, free-flowing electrons carrying the charge. Instead, the charge is carried by entire atoms or molecules called ions. These are just atoms that have a positive or negative charge, and they are literally physically swimming through the liquid to move that electrical energy around. Honestly, the best way to picture this is to think of the solution as a highway. But instead of electrons, the cars on this highway are the ions. They're the ones carrying the current from point A to point B. And it's pretty simple. The more cars you have and the faster they can move, the more current you're going to get. But not all chemical highways are created equal. And this is where it gets really interesting. With something we call a strong electrolyte, like salt, basically all the molecules break apart into ions right away. So as you add more water, things get a little better because the ions have more room to move. But with a weak electrolyte, like vinegar, most of the molecules stay together. When you add water, it actually encourages more of them to break apart, which creates this sudden surge of new ions, a massive traffic jam that causes a huge jump in conductivity. Now, this next part might feel a little backwards at first. When you dilute a solution, add water, you're spreading all those ions out. So if you were to look at any one little section of the liquid, there are just fewer ions packed in there. That means the overall conductivity, which scientists call kappa, actually goes down. But here's the flip side. Even though those ions are more spread out, they now have way more freedom to move without bumping into each other. It's like going from a gridlocked street to a wide-open freeway. So the conductivity per mole, basically how well each group of ions does its job, goes way up just because each individual ion can move so much more easily. So we know that electricity can move through a solution. But the real question is, can we actually predict how much juice, how much energy a chemical reaction can give us? Absolutely. And this is where electrochemistry becomes this incredibly powerful tool for predicting the future. And that brings us to a super important tool, the Nernst equation. Now, don't worry, we're not going to get lost in the math here. But what this equation does is absolutely critical. It lets us take the perfect textbook voltage of a reaction and adjust it for the real world, where temperatures change and concentrations aren't perfect. And this is why it matters. This is literally why your phone battery dies. As you use it, the chemical soup inside is changing, and that causes the voltage to drop. The Nernst equation is the formula that predicts that drop. It tells us the actual, real-world voltage of a battery, not just what it could be in a perfect lab setting. All right, so all of these reactions happen inside things we call electrochemical cells. And it turns out there are really only two main types, and they basically do the exact opposite things. So on one hand, you have the galvanic cell. Just think of a regular everyday battery. It takes a chemical reaction that wants to happen all on its own, what we call a spontaneous reaction, and it turns that chemical energy into useful electricity. But on the other hand, you have an electrolytic cell. This one does the opposite. It uses electricity to force a reaction that wouldn't happen otherwise. This is exactly what's going on when you recharge a battery. Okay, get this. Here's a really cool real-world quirk. If you look at the textbook numbers and you pass electricity through salt water, you should get oxygen gas bubbling up. But you don't. You get chlorine gas. So why? It's because of something called overpotential.
It's like some reactions need an extra little electrical shove to get going, and in this case, it's just easier to shove chlorine into reacting than it is for oxygen. This little quirk is a huge deal in industrial chemistry.
All right, let's bring all this theory down to earth. Now we're going to see how all these ideas are humming away inside the batteries that run our lives, and also in the corrosion that's constantly trying to break things down. So first up, primary batteries. These are your use once and toss 'em batteries. A classic AA battery, for example, is a dry cell. And what's wild is that its own zinc casing is the negative terminal, the anode, which literally gets eaten away as the battery is used. Then you had the mercury cell. You used to find them in watches. And they were amazing because their voltage was rock steady. It wouldn't fade out, it would just stop. And then we have our secondary or rechargeable batteries. The lead-acid battery is that big, heavy base in your car that gives it the power to start. And for ages, nickel-cadmium or NiCad batteries were the go-to for rechargeable electronics. They were tough and lasted a long time, right? Before the lighter, more powerful lithium-ion batteries that we all use today pretty much took over the world. Now check this out. This is pretty mind-blowing. Fuel cells, which were famously used to power the Apollo space missions, are a really special kind of electrochemical cell. Instead of just burning fuel to make heat, which then turns a turbine, which is super inefficient, fuel cells convert chemical energy directly into electricity. And as you can see, that direct conversion makes them way, way more efficient than your typical power plant. And finally, let's talk about something we'd rather avoid: corrosion. Rusting is, believe it or not, just a tiny, unwanted electrochemical cell that sets up shop right on the surface of iron. One little spot on the metal acts as the anode, where the iron actually dissolves, and another spot nearby acts as the cathode, where oxygen and water react. And that little flow of electrons between them is what creates that reddish-brown stuff we all hate: rust. So, we'll end on this thought. We have this technology, fuel cells, that are way more efficient than our standard power plants. They've been proven to work in space, the toughest environment there is. So what's the holdup? Why aren't they powering our future right now? Well, the answer really comes down to challenges with cost, materials, and building out the right infrastructure. A lot to think about. Thanks for joining me on this one.